Here. Today's speaker is Viktor Yuskovych. Please.
Thank you. Hello. Okay, 1 second. Okay, can you hear the presentation now?
Yes.
Okay. I am a PhD student in Kiev Polytechnic Institute. I study asymptotic behavior of solutions of stochastic differential equations in multidimensional space. Okay. Okay, I want to say what I mean by asymptotic behavior. Let's consider firstly one-dimensional case. Let X be a solution of one-dimensional autonomous stochastic differential equation of this form, where A is a drift coefficient and B is a diffusion coefficient, and W is a Wiener process. So actually, under some natural conditions about coefficients A and B, there are only two options about the asymptotic behavior of the solution X of t. It can whether go to infinity when t goes to infinity, or it can be so-called recurrent. So I study the conditions of recurrence. Oh, no, sorry, the conditions of transience. Transience means that the absolute value of the solution goes to infinity when time goes to infinity, almost surely. And recurrence means that the solution visits a neighborhood of any point infinitely often, almost surely. So yes, I study mainly the problem of transiency. So the first problem for a one-dimensional SDE is to find sufficient conditions such that the absolute value of X of t goes to infinity as time goes to infinity almost surely. And the second problem is the next. Supposing that the solution is transient, find sufficient conditions such that this solution X of t is equivalent to some non-random process X of t, which is a solution of the ordinary differential equation of the form dx of t equals ax of t dt. It means
with the same age.
Yes. So the question is when this noise is small enough that it doesn't affect the asymptotic behavior of the solution. So both these problems are studied in, for example, in Gihman-Skorokhod book, and Gihman and Skorokhod initiated to study this problem. So let's see the solutions of Gihman and Skorokhod. So the first problem is about transiency. Suppose that the diffusion coefficient is positive and the stochastic differential equation 1 has a unique solution for every starting point. Define a scale function of this form. So this S is called a scale function, and it is constructed using coefficients A and B of the equation 1. And depending on the behavior of this function, we can determine the asymptotic behavior of the solution X of t. Notice that the function S is increasing And there are several options. For example, this function can be unbounded from below, but bounded from above. In this case, we can prove that the solution x of t goes to plus infinity as time goes to infinity almost surely. When this function s is bounded from below but unbounded from above, then the solution goes to minus infinity. So in some sense, the solution goes in such a direction where this function is finite. If it is bounded from both from below and above, then it's known that with some probability, some positive probability, this process x of t goes to plus infinity, and with other probability, it goes to minus infinity. So in general, it is a transient. So absolute value of x of t goes to infinity. So in these three cases, the solution is transient. And in the case when this scale function is unbounded from below and unbounded from above, then the solution is actually recurrent. And in one-dimensional case, we can say it is oscillating. That means that the limit in superior equals plus infinity and limit inferior equals minus infinity almost surely. Okay, and let's study the solution of problem 2 about the exact asymptotic. Let the next conditions about coefficients of the SDE1 hold. Drift coefficient a of x is equivalent to some power function ax to the power alpha, where a is positive, alpha between -1 and 1. Let diffusion coefficient b be bounded and is not equal 0 anywhere. And suppose that the solution x of t goes to plus infinity almost surely. Also, let's consider the ordinary differential equation dx of t equals ax to the power alpha of t dt. So it's like the stochastic differential equation one, but we replace a coefficient with this, it's asymptotic power function, and just remove the noise. And we can find the solution of this ordinary differential equation. It is of the next form.
X0 is x sub 0, not 1. Or 1 in the parentheses. So look at this formula and the next one.
Okay. Yeah, I see. So here x of, well, I see. It doesn't matter what x0 is, but if x0 is 1, that here just 1. So I tried to write this in general for general x0. Okay, but I think you understand. And the idea, well, it doesn't, no matter which x0. So actually the asymptotic of the solution of ODE, x small of t, is this function. And the theorem of Dihman-Skorokhod states that under these conditions, the solution of stochastic differential equation is equivalent to the solution of the corresponding ordinary differential equation when t goes to infinity. That is. Okay, so I'm going to study the same problems in multidimensional space. So first, let's study some auxiliary results. Let Xi be a solution of one-dimensional non-autonomous SD. Non-autonomous means that now the coefficients A and B depend on T. And also by writing here omega, I emphasize that these coefficients A and B may be random. Suppose that a starting point Xi0 is x0, which is some non-random constant, and suppose that B is bounded. For this SDE, define the operators, which we can call generators. So for each T, we have so when we don't have T, we just have one generator L, but when we have dependence on T, we have a family of generators LT of S of X, LT of S. Okay. And define the exit time.
I have a question.
Okay.
In the SDE, you have coefficients A and B, which depend on 3 variables. And in the second, when you speak about generator, you have now some functions A and B, which depend now from 2 variables.
Okay, in this generator definition, A and B also depend on omega, but well, I don't write, but just
So these are random operators.
Yes, random operators, it's correct.
Mm-hmm. Mm-hmm.
Okay, and define the exit time, tau. Okay, exit time from the interval x1, x2. Okay, let's study 2 lemmas. Lemma 1. Lemma 1 says that tau is finite, almost surely under some conditions. Suppose that there exists a non-random function u, such that almost surely the values of these generators for each x from the interval, I think open interval must be here, and for all t is less than -1. Then we have the next estimate for expectation of tau, that is expectation of tau less than 2 maximum of absolute value of u on the interval x1, x2. Consequently, tau is finite almost surely. Okay, let's see the proof. It is classical and it is not difficult. So we have the stochastic differential equation for psi. Okay, omega dt plus b psi of t dwt. So the idea is to use Ito formula to find d u of psi of t. So use Ito formula, and after this you get actually you will get generators L t u psi of t. The generators will be in front of dt, and plus b psi of t u prime psi of t dw of t. Then write this in the integral form. So here will be u of psi of 0, which is u of x0 plus u of x0 plus integral 0t here s plus integral from 0 to t b psi s. Okay, then then substitute tau, t equals tau. Well, I just described the idea, and take the expectation. But to be honest, to say that this equals 0, you need to substitute first tau minimum n, for example, and then say that n goes to infinity, and then you can say that this is equal to 0. And after this, let's use that this generator is less than or equal to -1, and get that it is less than or equal to u of x0 minus expectation of tau. So expectation of tau is less than or equal to u of x0 plus expectation u of psi of t, and it is estimated by, as I have in the lemma, to maximum of u of x in the interval x1, x2. That's it. Lemma 2 is similar in proof. Also, okay, lemma 2. Lemma 2 allows to estimate the probabilities of exiting from the left side or right side of the interval. Let the conditions of lemma 1 hold, and let there exist a decreasing function s such that the generators now is less than or equal to 0. Then we have the next estimations for probabilities. For example, probability that psi of tau equals x1, which means that the solution when solution exists, this interval, it exists from x1 point, is estimated from above, and the same estimation from below. The proof is similar. Also, just use the Ito formula to find ds of psi of t. Actually, these results are from Gihman-Skorokhod, but I generalized these results a little bit. In Gihman-Skorokhod, they consider autonomous SDE, and they have equal signs instead of inequalities. Okay, now let's discuss my main problem.
Victor, may I ask a short question regarding lemma number 2? Why do you need the result of lemma 1, actually the existence of function u? So am I right here? You use only the fact that the expectation of tau is finite?
Yes.
Or you also need the actually?
No, I think I use only that the tau is
okay.
finite, almost surely.
Okay, thank you.
Okay, my main problem about the asymptotic behavior of a solution of a multidimensional stochastic differential equation. Let X be a solution of n-dimensional SDE. N is greater or equal to 2, because n equals 1 in some problems is special case. Autonomous SDE. where W is a m-dimensional Wiener process and B is non-degenerate in this sense. Okay, I want to say and notice that it is a vector equation because it is n-dimensional and the coefficient A is n-dimensional, which means that it is n by 1 vector. B is a matrix n times m, and since W is m-dimensional, then this is m times 1. Okay. To study asymptotic behavior, it's convenient to consider radius process and angle process. In some sense, to go to polar system in n-dimensional space. Define the radius r of t as absolute value of x of t, and define the angle phi of t as x of t divided by absolute value of x of t. It means that r is a one-dimensional process, and phi in this definition is a m-dimensional process. Actually, the values of phi are points on a unit sphere in n-dimensional process. And we can interpret these points on a unit sphere to be like angles or directions. Sometimes in two-dimensional case, some authors, for example, Spitzer or Friedman, they study angle in different sense, because in two-dimensional case, this phi is a point on a circle, but sometimes they consider two-dimensional case and consider this angle phi of t to be a common angle, polar angle in polar system, which is of the form arctangent. Let's say x2 divided by x1 of t plus some number of pi. Actually, if you have a process and on a plane and want to consider its angle, then you should consider its spiraling. You should consider the number of turns around the origin. So, for example, if the solution makes, for example, 2, so it starts with angle 0 and makes 2 turns around the origin, that the final angle is not 0 but 4 pi, for example. So you need to consider spiraling. And
so they consider continuous version of the angle.
yes, this phi must be continuous.
Do you need this discussion about rotations in your stuff?
In my what?
In your framework, do you need this discussion about rotation?
No, I just need to.
Okay, so please continue with you.
Okay, I would like to say that Spitzer studied this, and also Friedman. Okay. So I study asymptotic behavior of the solution X in the next sense. So I solve the next problems. Find sufficient conditions such that almost surely r of t radius goes to infinity as time goes to infinity. Find sufficient conditions such that there exists a limit angle. So the limit, almost sure limit of phi of t when as time goes to infinity. and find the exact asymptotic r small, such that the solution for radius r of t is equivalent to r small, which may depend on the limit angle phi infinity. Okay, so I started with n-dimensional autonomous SD with coefficients a and b. So now I want to study radius and angle. So I would like to write equations for radius, stochastic differential equations for radius and angle using Ito formula. Okay, so okay, in 2 words, I used Ito formula, actually multidimensional Ito formula to find, for example, differential of R, and write this in this pretty form using radial and tangential components. And also I used multidimensional Ito formula for each coordinate of phi. So you remember that phi is a vector. So this stochastic equation is actually a vector equation. So I write Ito formula for d phi 1, d phi 2, and so on, d phi n, and then grouped this in one vector equation. So here a rad is the radial component of vector field A at point X. Let's see what it means geometrically. Okay, let we have origin here and some vector field on a plane, and let it be, let this be the vector A of X. This will be the point X. This vector f A of X. To find its radial component at this point, we need geometrically to draw such ray, then find the projection of this vector on this direction, and this vector will be a rad X, radial component. And this is actually what this formula says. And tangential component is such component that radial component plus tangential component equals the vector field. And the same radial and tangential components we can define for matrix B. The same way, I can write B here, and define, for example, a radial component of B. So let's see, B is a...
Maybe let us continue, because most of us know how to apply Ito formula.
Okay, I continue. Okay, the first problem is the transiency of radius. I don't want to work with such coefficients which I obtained using Ito formula. So I, in future, further, I will consider such equations in general form for radius and angle. So let the equation for radius has such coefficients, mu, sigma, and phi. Equation for phi has coefficients nu and he. The same way like before, let's define the operators for the radius equation. L of v, phi, and phi. Okay. Theorem 1. Suppose that for every x0, there exists a unique solution, R phi of the system, which is a strong Markov process. For example, if we have coefficients mu and sigma to be locally Lipschitz and of linear growth. The second, let this coefficient sigma, oh, I'm sorry, I forgot to say what is W prime. So actually, in this equation, we have an m-dimensional Wiener process. So this must be, I think, a vector. But in future, I need sigma to be a scalar. So I can find some Wiener process W prime, one-dimensional Wiener process, and one-dimensional, so that is scalar sigma. Okay, so suppose that this sigma is positive. And
but let me ask you, what is the relationship with this new Wiener process with the old one, which you initially have the stochastic differential equation in the d-dimensional space, and you have already a vector valued Wiener process. What is the relationship with those Wiener process? You said I can find. What does it mean?
I can try to write this relation. So 1 minute. Okay.
You may write it in abstract form if you have some coefficients A1, A2, AM with DW1, DW2, DWM.
Yes, so actually, let's say that we have firstly this sigma to be a vector. Well, sigma dw and w is a vector. Let's consider the integral. So actually it is integral of sum k from 1 to n m sigma k and so on. And I think it is Levy theorem. Maybe I'm wrong. So you can find a one-dimensional Wiener process. Okay. With some sigma, one-dimensional sigma, you can find such sigma in such a Wiener process. I think I can write the relation between sigma and this sigma, but it's technical. I think everybody understands.
Okay, I just asking because I was worried about the flow of sigma field. Now it is understandable that your new Wiener process is adapted to the old flow of sigma field.
Okay.
Viktor, may also I ask a very short question? As I understand, you will not consider this equation as a system of equation. You don't care about the quadratic variation between the two Brownian motions, right? Because before you had that, okay, the first equation and second was driven by the same Brownian motion, but now you just took another Brownian motion, and it seems that the quadratic variation of new Brownian motion and old now should depend also on solutions to the equation. So therefore, you don't care about that, right?
Yes, I don't care. Now I study actually the equation for R and say that this phi of t is just, so I can say that this coefficient mu is dependent of R and t and omega, for example. Okay.
Actually, it was the reason why you formulated your the first lemma for random coefficients, right? Because
Yes,
after
correct.
that your coefficients are random. Okay, thank you.
Okay, so theorem. Condition 3. Let there exist a non-decreasing function, let's say Lyapunov function, v0, which is infinite at 0, and for which this generator L is less than or equal to 0, and in the neighborhood of 0 for all phi. And let there exist a decreasing function v infinity, such that it is finite at infinity, and at the neighborhood of infinity, it is less than or equal to 0, as we need in those lemma and that lemma. Then, almost surely, r of t is greater or equal to 0, and r of t is, well, not transient, but r of t goes to infinity as time goes to infinity. Actually, condition number 3 implies the first result, and condition 4, in some sense, guarantees the second result. Actually, instead of finding two Lyapunov functions v0 and v infinity, we could try to find some common function which has these properties at 0 and at infinity, but it's not so easy to find such a common function. So let's say that there are two functions. Okay, let me say that let me discuss only the idea of the proof. So 0 t, and here we have delta small and delta capital. So
the line is not T line, but R line.
Yeah, thank you. Yes, R. Okay, so there are several steps in my proof. First, let's say that the R of 0 is in this interval. So I set some small epsilon. I prove that I find the probability that the solution exceeds this interval from the right, and then set epsilon to 0. When the solution, then I use strong Markov property and say that let the solution is here, and also use lemmas to find the probabilities to go out from this interval from the left and from the right. And if we go to the left, I say it is failure, and this probability is positive, and probability of going to the right is also positive. And if we repeat this process many times, then at some time we can reach this level delta. And using the condition, using this Lyapunov function v of infinity and the lemma, we can estimate the probability to that R goes to infinity, but it's in 2 words. Okay. Okay, so this is
Victor, may also I ask, in the lemma number 2, I remember that you assume that also the stopping time is finite.
yes.
Is that clear?
I forgot to say about this. Thank you. Yes, it is finite. So if we consider any interval, R1, R2, let's say, then consider the exit time tau from this interval, then we can show that tau is less than infinity almost surely using lemma, because we can find such function as in the lemma, because our coefficients mu and sigma are continuous and therefore bounded. So I have the exact view of this function u.
And maybe sigma is positive.
Sigma is positive, yes, yes. Yes, so actually I have in my article that I write this exact expression for this function u.
The fact that sigma is bounded away from 0 suffices. I think.
You mean that it is not just positive, but less than or equal to some sigma greater than 0? Greater.
Yeah. Yes, but you don't assume it.
Maybe I forgot to say about it. Yes, I assume this, but no. Maybe I don't assume this. But if I consider a segment, then on a segment, on any segment of R1, R2, sigma is indeed like that.
Then you may just say that by Gersanov you eliminate the drift, and with sigma bounded away from 0 and bounded, you may change time, random change of time, and it's equivalent to some change time within a process, which of course has a tau finite almost surely.
Okay, I see. Thank you.
In brief.
Okay, I will think about this. Thank you. Okay.
Without any continuity, without anything.
Okay.
But still, you need to, as I understand, you need some bounds of the drift term, because if you have very strong drift.
Yes.
Victor, also I have another question, because I actually do not understand the formulation of this theorem. Actually, the condition number the result in number 1, that R of t is strictly positive. As I understand, you talk about the equation which was on the previous slide, but or probably two slides before, which you obtained after the applying of Ito formula, right? So, okay, Victor, may I reformulate my question? Here you just consider in the previous slide, I mean, where sigma and mu are and so on, you just consider just some equations, or you mean that this is the equation which you obtained after the application of the
no. Yes, this is okay. These new equations and these coefficients mu sigma has nothing to do with A and B. So I forgot about those.
Okay, then I understand this thing.
Yes, yeah, I forgot to say about this. Thank you. Okay, the next result is about radius lower asymptotics. I need this maybe some auxiliary result to find conditions of angle stabilization. So now I decided to get rid of this sigma diffusion coefficient and used Levi theorem to find new Wiener process and make a random time change A to write the stochastic differential equation for the radius in this form. So with unit diffusion. Actually, I write mu, but this is new mu. Yes, if I made a random time change, then this is new mu and new r, and but okay, in my article I write tildes everywhere, but let's reduce them. Okay, so further I consider this simplified SDE for the radius. Let in equation 4 the drift coefficient is of the form. It has this term, which is a power function r to the power alpha, where alpha is between -1 and 1, and mu is greater or equal to m, which is positive. And mu2 is, let's say, small enough when r goes to infinity, as I write here. Suppose also that the solution r is positive everywhere, so doesn't hit 0, and transient, and it goes to infinity at infinity. Then I obtained the next asymptotics, but it is just lower asymptotic, almost surely. Okay, let's move on. Angle stabilization. Consider the equation 3 for the angle. Suppose that r doesn't hit 0, almost surely. Suppose that we have such a lower asymptotic. And suppose such estimates for coefficients nu and he, like you see here. Then there exists almost sure limit of phi, which I denote phi infinity. The idea of proving this is to write phi of t in integral form. And write infinity, t equals infinity, and study the conditions of convergence of these integrals, of this Lebesgue interval and Ito integral. And these conditions are sufficient to the existence of phi infinity.
It seems to me that the first condition is extra, that you don't hit 0. Because if radius converges to infinity, then after some moment, nu and he are small enough, and this is enough probably for convergence of stochastic integrals.
Okay, thank you. Maybe. Okay, and the final result about exact asymptotics of the solution of the radius of the solution. Let the conditions of theorem 3 hold. It is about angle stabilization. And suppose also that this coefficient mu1, which is one term of a drift coefficient, when r goes to infinity, has the next limit. Mu1, I denote infinity phi. Then almost surely the exact asymptotic of r is the next. 1 minus alpha, mu1 of infinity. Here I substitute phi infinity times t to the power 1 divided by 1 minus alpha. And if you remember the one-dimensional case and Gieckman-Skorokhod theorem, it is something like that. Okay, the idea of proof is to consider some ordinary differential equations which bound the this r of t from below and from above, and they depend on epsilon. And when epsilon goes to 0, we have this result. Okay. Okay. So that's all what I wanted to say. Here you see references. Thank you for your attention.
Okay, but before we start discussion, let me ask you a technical question. You formulated last 3 results in terms of abstract coefficients. Do you have as a condition on the initial coefficients A and B of the initial equation when you can have the same conclusions?
Well, sometimes I have some examples and some relations with the initially with this equation x and coefficients A and B. Well,
can you show us some examples?
Yes. Okay.
Mm-hmm.
Okay. For example, in this theorem, I think that if we have vector field A such that A of x scalar product x is greater or equal to some constant times absolute value of x to the power alpha plus 1, where alpha is between -1 and 1, then I think theorem 1 holds, because this means that the drift coefficient A pushes from the origin.
But you must also have some conditions on the diffusion matrix.
Yes. Maybe let diffusion be bounded, then everything is okay.
Does it guarantee that you will have condition 2 that your sigma small will be positive?
No, it doesn't guarantee, but well, I'm not ready to give the the example in.
Okay, thank you. Now let us start our discussion. Maybe somebody have questions or comments, please.
May also I ask a very short question about your last slide, about your last statement. Could you
Yes.
go there? Could you remind what parameter alpha is here?
Yes. Alpha appears in this theorem.
Okay, I see. And my question is, what happens if alpha is equal to 1? Because it seems when alpha is equal to 1, you are even in the better situation. So can you say something here?
Okay, if alpha equals 1, then okay, it's obvious why I exclude 1, because here it will be division by 0. Well, alpha equals 1 is I think it's something like a linear equation, but I'm not sure. So no, I didn't study it. I didn't study this.
Because it
case.
seems that also there should be so very nice nice increasing, but probably with some different function. I do not know. I don't have intuition about that.
If alpha is 1 and mu is a constant, then you have exponential growth and you don't have equivalence as usually.
Do you have that some kind of phase transition? I mean, when you have for say alpha strongly less than 1, you have something like polynomial growth, and after when alpha is equal to 1, you have immediate exponential growth. Andrei Yuryevich, I cannot hear you. Andrei Yuryevich, your microphone is switched off if you say something.
Андрей, мы вас не слышим.
And if alpha is 1, then solution is this. And you cannot say that this function is equivalent to exponent of a times t. So initial condition is important. And here, if you write here plus constant, you have the same asymptotic as t tends to infinity. So alpha is 1 is really critical, and negative 1 is also critical. For example, if sigma is 1 and alpha is -1, then you get a Bessel process. And for Bessel process, you don't have asymptotics, deterministic asymptotics as t tends to infinity.
Okay, thank you.
And maybe let me make one comment. If diffusion matrix is a constant and drift is such that you have constant times x to the power alpha plus 1, then certainly you have asymptotics at infinity. And maybe let me explain why do we start to study such processes. I studied the following problems of small noise perturbations for stochastic processes of the form. Let us consider maybe at first one-dimensional stochastic differential equation perturbed by Wiener process multiplied by epsilon, and assume that the function a, for example, in a neighborhood of 0 behaves like some constant to the power x to the power alpha, so a plus for positive, a minus for negative, and if alpha is less than 1, then solution to the ordinary differential equation is non-unique, and you may go up and you may go down, or you may stay at 0, but if you add some small noise, then you get uniqueness. And the question is, okay, send epsilon to 0 and study a limit. And the idea was the following: we did some transformation of space and time. Look at this small. We look at behavior for small times, and we discover that in order to solve this problem and to find probabilities goes up and down, it's sufficient to study the following stochastic differential equation and behavior of xt as t tends to infinity and asymptotics of this xt. By the way, we also added multiplicative noise and multiplicative noise with integrals with respect to Levy process, whose Levy measure has some power asymptotics in the neighborhood of 0. And the result after the transformation was as follows: you have to study stochastic differential equation, maybe with Levy alpha stable norms, and asymptotics of this equation as t tends to infinity. And then we try to think what happens in multidimensional case, because if A is, say, bounded and just bounded and measurable, and you add multidimensional Brownian motion, then by Zwontkin-Vereytenikov theorem, you have a strong solution, a unique strong solution to the perturbed equation. And then we try to do the same. Okay, assume that A has some power asymptotics in the neighborhood of 0, but and we rescaled, and we got the problem, discuss what happens with this solution for t large enough. And the first step was, okay, assume that the coefficient A is such that it pushes out, it pushes outside of 0, and assume that it has some power asymptotics in the neighborhood of 0, but and you have some asymptotic, say A of x is equivalent to something that depends on, say, f of polar angle times radius to the power alpha. And it was not clear how to prove that x tends to infinity and how to guarantee that angle is stabilized. And there are a lot of other interesting problems. Viktor's theorem is about this case, that at infinity, the vector field A behaves like this repulsive vector field, maybe close to this repulsive, I forget, and multiply by x divided by x. Okay, push outside of. So his result is the following: is if this coefficient has the following asymptotics, then at first solution of xt converges to infinity, so absolute value converges to infinity, and the second result, that angle, there is a limit of angle, so you don't have infinite winding around 0. And when you calculate the limit of angle, then you say, okay, now insert this limit here and solve ordinary differential equation with phi this, and you get asymptotics for radius. But there are a lot of other possibilities that are also interesting, and I don't know how to solve them. For example, assume that the vector field has the following form, okay, r to the power alpha, and this vector field is, okay, assume that it has radial part and tangential part, and if you consider equation for polar angle, for deterministic equation, you may appear that, okay, that some points are like attractive or maybe repulsive in two-dimensional case, and in three-dimensional case you have a sphere and you have Poincaré-Bendixson theorem, for example, for limit cycles and so on and so forth. And the question is, okay, what is behavior of x of t? Do you have infinite rotation? Do you attract to some attractive point, or maybe, okay, assume that you have some attraction to some line here, another, okay, something like this. So this is our vector field. And the question is, can you infinitely often, is it possible that the angle infinitely often visits this line and this line, or it attracts maybe somewhere in infinity and never exits? So like Bayesian of attraction. So everything depends on the noise, on the speed of noise, and this problem is not obvious and is not solved yet. So I think this is for future investigation.
Okay, thank you. So you have this random limit for the angle up to now, and up to now you cannot say something about its distribution on the sphere. Yes.
No, we don't know how to. No, we don't have a distribution. But there are a lot of other questions. So
yes. Your questions are very related, because when you choose between the singularities or special points of or special lines or surfaces, subsurfaces on the sphere, where you want to have your limit angle, you exactly are discussing about its distribution. Yeah.
So in this case, I think the distribution will be absolutely continuous.
Yeah, interesting. Okay, thank you. Maybe some other questions or comments, please. I also have such a comment that when we discuss initial stochastic differential equation in a multidimensional case, there are some works where people can produce exact statement about the behavior. For example, a difference between two solutions. This is also about norm of the difference. This is very close. Norm of the difference between two solutions. It is exactly more or less the same case. And there are works of Lejan Watanabe and Zirbel-Polchinski devoted to isotropic stochastic flows. Then in this case, they can consider tangential and radial components of diffusion matrix. And they have exact statement about the behavior of the norm of the difference. Norm of the difference, again, is diffusion process, one-dimensional, and so on. So maybe it's good to think about these articles as a source of examples where the last statements can be reduced to the initial coefficients A and B.
Okay, I see.
Okay. So if there are no any questions, we finish our work for today. Thank you again. And Georgi, do you know who is the next speaker?
Екатерина Глиняная.
Okay. So see you next week. Bye.
Goodbye. Have a good day.
Bye.
Bye.